Hello and welcome to another variable acceleration question. This time this one is from the 2021 paper, Mechanics, and it's question 5. Now, these ones really aren't too bad. I'm going to answer once again why I know it's variable, why the acceleration is varying first, because if you know that, you just know what kind of things you're going to need to use, what techniques you're going to need to use to answer the question correctly. I know that because if I differentiate this, I get the acceleration. And the acceleration is still in terms of t, not on a j component. The j component looks like a constant acceleration after you differentiate it, but it's on the I component where you're going to get 3 over t to the minus 3 over t minus a half, and that tells me the acceleration is varying. So write down your little s, v and a, and remind yourself which way it goes round for differentiating and integrating. Differentiation goes down, integrate goes up one. Yeah, if you remind yourself about that, that's pretty much the whole of the question. Okay, we've got to find the acceleration at a time t seconds where t is greater than 0 first. Okay, so we're gonna, if I write this firstly as v equals 3t to the half and minus 2t, then I can easily see that the derivative of that is going to be 3 over 2t to the minus a half and minus 2, and then I've just got to find the acceleration of p at time t seconds. Well, there we go, I have done it. That is the acceleration of t at time of p, sorry, at time t seconds. So that's all well and good. That doesn't seem too bad for a first question. You might even, in a paranoid way, write it in terms of I and j if you really want to. Be my guest. I know what you mean there. But I must admit, I don't, having had scripts back from the markers before, I don't like how incredibly pernickety they can be about certain answers. You must show where you're working, basically, and I did actually send a letter to the chief examiner once asking if they minded if we worked in column vectors, and he said no, of course you won't be in any way penalised for that, which is good. And he said he did the same thing because I's and j's notation is really clumsy. Anyway, part B, find the value of t at the instant when p is moving in the direction of I minus j. Aha. Well, direction is always about velocity. Yeah, if it's talking about the direction it's moving in, it's all about velocity. And if it's moving in the direction of I minus j, well then I can say that my velocity vector, which is 3t to the half minus 2t, that must equal k times I minus j. Yeah, now I'm showing you, 1 minus 1, what we're doing, i's and j's in columns. Yeah, 1 minus 1. Now the reason I'm going to answer a question like this, there are other ways of looking at it, but this kind of comes up in other questions as well. Remember, if it's moving parallel to a vector, then it's a scalar multiple of that vector. You might not like the look of that, but this is a simultaneous equation because we've got 3 root t, because it's 3t to the half, well that equals k, but I also know that minus 2t is minus k, and so now I can eliminate k by just plugging in the values. That's the way I prefer to do these questions anyway. And so sure enough, I'm going to get 2t equals 3 root t, and therefore I'm going to have, if I square both sides, or I could just divide by square root of t actually, 2 root t, because t to the 1 divided by t to the half is t to the half, equals 3, and so t equals 9 over 4 after you've divided that by 2 and squared both sides. Okay, that's part B. Part C. At time t seconds, position vector p relative to a fixed origin is r meters. When t equals 1, r equals minus j. I don't like the way that looks. Once again, a lot of the confusion comes here from using I and j notation. R is 0 minus 1. In other words, at the point 0 minus 1 when t equals 1. And this is still the same object that we were dealing with earlier, p. And so let's find an expression for r in terms of t. Well, r is s. They are displacements. It's the general position of it. So we need to integrate our velocity vector there. And so we're going to get, I'll write it down as r because they defined r to be the position vector. So r equals, okay, right, let's integrate this then. We're going to increase the power by 1. Then we're going to divide by the new power. The new power is 1.5, and 3 divided by 1.5 is 2. plus a constant c1. And then we're going to integrate this, we're going to get minus t squared plus a new constant c2. Now we also know when t equals 1, r should equal 0 minus 1. So that's what I'm going to use next, yeah? So 0 minus 1 equals, let me just move over so you can see this nice and clearly. Okay, we're going to get 2 plus c1, so c1 must be minus 2. And we're going to get minus 1 plus c2, and so c2 is 0. And so now I know the general position. It's r equals 2t to the 3 over 2 minus 2, and then minus t squared. And that's the general position. And I've found the expression for r in terms of t. They might want me to write in terms of i's and j's, 2t to the 3 over 2 minus 2i, and then plus minus t squared j. I still think it looks a lot more ugly with I and j. It looks nice and clean in a column vector notation. Okay, so yeah, probably if they use i's and j's at the start of the question, out of courtesy really, I'd put it in i's and j's at the end. It seems sensible, but I massively prefer columns. Okay, find the exact distance of p from the origin at the instant when p is moving with speed 10. Okay, the speed is 10. Now let's recall the velocity vector. The velocity vector was, I can't remember, let's recall it though, we need it, 3t to the half minus 2t. Now we want to find the exact distance of p from the origin when p is moving with speed 10. So if this has got speed 10, that's the length of the vector. So I need to do 3t to the half squared plus minus 2t squared square rooted is 10. And so that's going to give me 9t plus 4t squared. And if I square both sides, that will be equal to 100. And so you've got 4t squared plus 9t minus 100 equals 0. Yeah. Now you've now got to find what this factorizes to give. Well, if we have a t minus 4 here and a 4t minus 16t plus 25 here, we can see that t equals 4, or t equals minus 25 over 4, but that gives a negative time, so we want t equals 4. So it happens when t equals 4. And now we've got to find the distance from the origin. Well, we know what r equals. We can use r from our previous answer. And so r equals, when t equals 4, I'm using this right here to work this out. Okay, 4 squared is 2, cubed is 8, times 2 is 16, minus 2 is 14. And then 4 squared is 16, minus 16. And so the distance from the origin is Pythagoras, basically. It's going to be equal to 14 squared plus negative 16 squared square rooted. That's 256 plus 196, which is root 452. Did they want the exact distance? Yeah. And so that will do. You might simplify it. I think my calculator is telling me it's 2 root 113 meters. There we go. Okay, that's all there was to that one. I hope you enjoyed the video and find it useful, and yeah, keep up the hard work. Bye bye.